Hello and welcome to our next lesson of calculus and vectors. Today's lesson is sketching planes in R cubed. This lesson is split into two parts, so there are two different documents and two videos for it, so please make sure you're watching both and completing both. Because the concepts covered were very different, I did decide to split them into two parts, but they are required for this unit as a whole, so please make sure you are completing both. Today's lesson, though, in this part, we are looking at sketching planes in R cubed. So by the end of this lesson, you will be able to interpret and sketch planes in R cubed using their Cartesian equation as well as geometric properties that we're going to see. So before we get into R cubed, we are going to look at the different interpretations of a graph with the equation x is equal to 4. So we have looked at R squared, and now in this course you got introduced to R cubed, and way before that you saw just R, which was your number line. So given x is equal to 4, in the R space, so our one-dimensional space, this is just our number line, which means you will have a point on the number line. And this point will have an x value of 4. Now, when we added the second axis here, so we had the xy plane in R squared, then when we had x is equal to 4, we now had a line, a vertical line where any point on this line will have an x value of 4, but you can have infinitely many points by changing the y value. Now, in R cubed, we have another axis, which is our z-axis here. So when you have x is equal to 4, that means, again, that your x component for any point will be the same, which is 4. And in this case, you will have a plane. This plane is parallel to the zy plane, as you can see here. And all the points, or any point on this plane, having the coordinates x, y, and z will be starting with 4, and we have y equals s and z is equal to t for a random point on this plane. And this point, or this plane, will also intersect the x-axis at 4, 0, 0. And because it is parallel to the y and z axis, it will have no point of intersection with either of those axes. So now in R cubed, because that's our goal, we're sketching planes in R cubed, I'm going to show you the case with x, y, and z when you just have a single equation, which is, for example, x is equal to 5, y equals 6, or z equals 6. So you have one variable in the Cartesian equation of your plane. In each of these cases, you will have that the plane is parallel to one of your other main planes, which is either your xy plane, your yz plane, or your xz plane. So this is exactly as we just saw up here. When x is equal to 5, this is parallel to the zy plane, and it has a point of intersection, and exactly as we wrote here, at 0.500. In plane 2, when you have y is equal to 6, that means your y is constant, and it is 6 for any point on this plane. This plane is parallel to the xz plane, and it has a point of intersection with the y-axis at 0, 6, 0. And finally, when you have z is equal to 6, then that means your z component is constant, and it is 6 for any point on this plane. And so this plane is parallel to the xy plane, and it intersects the z-axis at 0.006. So anytime you're given the Cartesian equation of a plane where you only have one of the variables defined, so either x, y, or z, and it is equal to another value, this is how you can draw the sketch for it. And remember, a plane is sketched using a parallelogram in all of these cases, or in this one, it is a square because just of the position. And so you will be able to sketch any equation of this form. The second, and just here, just to put that all together, generalizing it when it is x is equal to a, y is equal to b, and z is equal to c. And the reason we use a, b, c is consider, and I will give you a refresher of this because we will use it a lot in this lesson. The Cartesian equation is ax plus by plus cz plus d is equal to 0. This is the Cartesian equation of a plane. So that's why usually x will correspond to lowercase a, y will correspond to lowercase b, and z will correspond to lowercase c. Now, the second type of equation that you will see and you will be asked to sketch is when you have two variables defined. So here we have x and y, and so there's no z, and there's also no d component here as well. So that d scalar, we do not have a d here. So the first thing we know, and this will work for any of these types of equations, so even if you have 5x minus half of z, or if you have square root of 3x, oh, no, I used x. So let's say this is y, and then just minus z. So in either of these, or in all of three of these equations, I hope you can see that the origin lies on these planes, because if these two are 0, or two of your or all of your variables are 0, then this equation is satisfied. All of these will be equal to 0, and so the Cartesian equation is satisfied, so the origin does lie on these planes. So that's already one point you have. And so that's what is written here. So any point of the form 0, 0, and c here, because you can pretty much choose any value of c, will be on this plane as well. Because if x and y are 0, then it doesn't really matter what our z value is. This equation will be satisfied regardless. So c can be any value when x and y are 0. And so what this tells us is that any point on the z-axis, and consider any point on the z-axis will be of the form 0, 0, c, is actually a point on this plane as well. So going back to intersections of a line and a plane, then we know that the z-axis lies on the plane. So the plane will also, we can say it contains the z-axis. Now, we find one more point on our plane, and so we interpret from 2x minus y. We just rewrite this as y equals 2x, because this was equal to 0. And so any point that satisfies y equals 2x will be on the plane as well. So one example could be 2, 1, 0. So if we pick a, sorry, this should be 1, 2, 0, my bad. 1, 2, 0. So same here. This will be 1, 2, 0. Because when x is equal to 1 and this produces 2, then y will be equal to 2. And again, any value of z here works, but we just wanted to pick one point, and we picked it that it is on the xy plane. So now when you are sketching this, again, we know that the z-axis is on this plane, and here is that other point that I found, which was 1, 2, 0. So knowing that this is one of the sides of my parallelogram, I will draw from the origin to this other point I found, and now you are just completing the parallelogram because you have two of its sides. And so that is how you would sketch any equation of the form where you have two variables and no d value defined. The next example we see is now you have two variables, but you do have a d component. So in this case, we can no longer say that the origin is on this plane, because if you have 0, 0, then you have that negative 10 there. So this does not produce equality on both sides. So then we don't actually have the case where now the z-axis is on our plane again. However, we can still find some points in order to be able to draw out the plane. So we write this as 2x minus 5 is equal to 10. And so now you're just have to pick some points of x and y that will satisfy this. And the easiest way to do this is to find the x and y intercepts, because you can just let x be equal to 0 and find what y is, and let y be equal to 0 and find what x is. So when y is 0, the x-intercept will be 2x is equal to 10, so x is 5. So that means the point 5, 0, 0 is on the plane. And similarly, when x is equal to 0, the y-intercept will be negative 5 is equal to 10, which produces y equals negative 2. So the point 0, negative 2, 0 is on the plane as well. And so this is exactly, I did mention this part, but because now we know that the z-axis is no longer on our plane, we do consider when x is 0 and y is equal to 0, we get the equation 0z, which is technically the coefficient of z, we just don't write it, minus 10 is equal to 0. But this does not hold true for any value of z. So then we actually have that the plane is parallel to the z-axis, which means it doesn't actually intersect with the z-axis, but they are parallel. And this will help us find one of the direction vectors for our plane, knowing that it is parallel to the z-axis. So pretty much the value of z does not impact our equation at all. And so z can be any value here, and this will not impact any of our points. So as long as x and y satisfy this equation here, you will have points on the plane. So going back to these intercepts that we found, I can pick any value of z here, and I will still have 5, 0, c. This will be a point on the plane. And same here, 0, -2, c will also be any point on the plane as well. So what does that look like now? So this is that parallel side to the z-axis. And here is point 0, -2, 0, which is our y-intercept. And going back to that 0, -2, c, this is pretty much just moving up and down along this line. So any of these values will be on this plane. Keep in mind, this plane is extended infinitely in all of these directions, so this way as well. So we only just draw the parallelogram, but you do have to remember that it does extend because it's a plane. And same with this point here, which is our x-intercept 5, 0, 0. So having point, and this could be 5, 0, c, for any value of c. And again, you're moving up and down on this portion of the plane, and all of those points will hold true as well because the value of z does not affect our equation. And so here's that also parallelogram, so our sketch is complete here. Now, if you also had, for example, your y was positive, you can do the same thing. You would just draw this line and go this way. Make sure this is parallel. Or maybe I should do this with a different color. Red is better. Okay. And that's, for example, how you would draw the plane if it had a positive y-intercept. And again, if it had a negative x-intercept, you can also extend it this way and draw your parallelogram that way. So just an observation here. So using the same idea, if A, C, and D are non-zero, and no, I didn't show you for this. So this would be the case, like, for example, you have 3x minus 5z plus 4 is equal to 0. So you see there's no y value here. So then the resulting plane is parallel to the y-axis, and the value of y will not affect our plane. And similarly, when b, c, and d are non-zero, so when you have, for example, square root of 3y minus 4z minus plus 8 is equal to 0, and we see that there's no x component here, so then this resulting plane is parallel to the x-axis, and so any value of x will not affect our plane. And so you can now sketch any plane of this format. Now, another example that we have, another case, is when you have A, B, and C defined, but again, no D here. So no D, or D is actually better mathematical language would be D is equal to 0 here. So the way you find this or sketch this, you find 3 points on the plane, and these 3 points actually uniquely identify the shape of your plane. And the easiest way here would be the x, y, and z intercepts. But for example, we can also see right away that the origin is a point on this plane because 0, 0, 0 would produce 0. So that's already one of our points. So another point we pick will be when y is equal to 0. So, or sorry, starting with this one, z is equal to 0. So in this case, you have x, y, and 0, and we want the equation to be satisfied by this. So here, if z is equal to 0, you have x plus 3y is equal to 0. So here you have your choice of x and y to pick, and go with the simplest option. So if x is -3 and y is equal to 1, then -3 plus 3 is equal to 0. So then you have the point -3, 1, 0. For example, you could have also done x is equal to -6 and y is equal to 2, and that still would have been a point as well. Then a third point we pick, you can let y equal 0 this time. And then you have the point as the form x, 0, z. So in this case, x minus z is equal to 0, again from the Cartesian equation. So here, simply we pick x is equal to 1 and z is equal to 1. So now we have point 1, 0, 1. So now I plot those 3 points. So I had the origin, here is point B, and here's point A, and all you do is connect them. So in this case, you don't actually need a parallelogram. So just the triangle in itself will suffice as the shape of the plane, and that's it. You would be done, and that's your sketch right there. So again, when D is equal to 0, now you have a method for finding 3 points and then being able to sketch the graph. Now, our last example is when we have A, B, C, and D are all non-zero. And now we rearrange and we just move the D value over. So we have 2x plus 3y minus z is equal to 4. And in this case, again, the simplest way is to find your x, y, and z intercepts. So we find the x, y, and z intercepts are respectively 2, 4 over 3, and negative 4. And these corresponding points are 2, 0, 0, 0, 4 over 3, 0, and 0, 0, negative 4. And again, similar to above, you plot those 3 points and you connect them using a triangle shape, and that would be the sketch of your plane. Because really this could also be extended to be a parallelogram, but that will suffice for your sketch. And so now you've seen all the different cases for how the Cartesian equation could be presented, whether you have different values of A, B, C, and D defined for you, and you'll be able to sketch these planes. And again, these are hand-drawn sketches, so they don't have to be exact, but you do have a method to be able to sketch them. So you have some practice questions here as well. And again, don't forget, if you haven't already, complete the other lesson for lesson 47. And that's a wrap for today. Check Google Classroom for any other tasks. And if you have any questions, don't hesitate to reach out, and I'll see you all next class.